Hey, it's Craig here at the ValveStudio. I just got finished mixing together today's episode. It's an hour long, and when I got done, I was like, "Wow, it's man, who's going to watch this?" But it took that long because I introduced a really good tool to learn how the intricacies of placing the load line on a triode amplifier. And I have an interactive example that I'm going to show. It takes me about 30 minutes to get through it. And it's a tool that you can use for your own designs. So stick with me through this whole hour. You can skip the introduction if you want. But you just get to the part where you're running the ipython notebook. And I encourage you to follow along and do that. Run it on your computer there while I'm doing mine. So thanks for watching. Let's get started. Welcome to the ValveStudio. Our work continues on this Mectron record player to convert it into a guitar amplifier, a little practice amp, maybe about 3 or 4 watts. I'm not simply adding a speaker jack to this and a guitar cord jack to it. I'm actually doing a complete analysis of this. So last time, if you watched, what we ended up doing was we went through and we looked at the data sheets. We found the bias point for where this thing operates, and then we went and verified it by measuring all the voltages and currents. And we got very close to our estimate of the bias point from the data sheets themselves. Now today, what we're going to do is we're going to look at the load line. We started talking about what the load line actually represented. We're going to look at the AC load line. So in order to do that, we need some additional measurements taken over here. We'll talk about those in a minute. And then we're going to go back to the data sheets and do some drawing on data sheets. And that is the traditional approach to doing a design. You find the bias point, and then you know the impedance of the speaker you want, and the reflected impedance through the output transformer based on the turns ratio, and that helps you, with your design. We're not going to use any paper today. I actually came up with an interactive demo that you can run while you're watching this video, and I encourage you to do that. The interactive demo lets you tweak every aspect of placing the load line and looking at all sorts of different types of circuit behavior because of that. It's something I've been working on for a couple of weeks now. It's a great educational tool. And when I got it running, I sat there and played with it. I've played with this thing for quite some time, looking at different scenarios. What if I had an 8-ohm speaker? What if I had a 4-ohm speaker? What if I had 2 4-ohm speakers? What if I changed the turns ratio? What if I made the plate voltage a little higher? Those kind of things. It's really very simple to do on this tool. And there's no software to install. You can just run this thing right off of Mybinder, or if you want to, you can download the whole thing from GitHub and run it with Jupyter Notebook. So there's 2 references I want to talk about. If you want to do some further reading, there's 2 references that I got a lot of information out of. One of them is from the Valve Wizard. And if you look at his single-ended output page, there's a complete description of how he ends up recommending doing it. And there's some kind of critical points in there that you may want to look through either before we get started here today or afterwards. And then there's another one out there from Steve Bench. That's a PDF document. It covers additional information about placing the load line. So those are both really good references, and those are listed in the show notes as well as on the in the notebook, the ipython notebook. In order for all this to get started, I needed the turns ratio of my output transformer in the Mectron record player. So because I had a working amplifier, I didn't drive it with a variac, which is what a lot of other people do. I just put a sine wave right into the amplifier, and I dialed it up, and I measured the primary side voltage, and then I measured the in RMS, actually I make sure I was in the middle of the bandwidth. So then I dialed it up, and I got the primary voltage in RMS, and then I got the secondary voltage in RMS, and divide the 2, and that's the turns ratio. For this output transformer here, my turns ratio is 33. So I got all this worked out. I got it all done probably about a week ago. And then at lunch, I was cooking lunch, and I was watching a video from Dennis Carter. Dennis Carter was going through some of the similar type of things that we're going through here. And he has a slide on his on a paper where he talks about total harmonic distortion. And he has a really simple calculation for that. And a lot of the videos and a lot of the content that's out there, they're all pretty much use simplistic algebraic expressions for determining circuit performance. And whenever I see that, I'm like, well, where did that come from? Because that's either an approximation or it's a rule of thumb or it's something like that. And I want to learn a lot more about where these fundamental design equations that all these tube amplifier designers are using to find out, where did that really come from and what are the assumptions that made that approximation legitimate. So I started out, I looked at the RCA receiving tube manual. I have the RCE22, which is from 1963. Now you can download this book over at tubebooks.org. And I found on page 19 here, I found, let me see here. Yeah, so I found that the percent distortion, and they go and they look at basically your on the load line, you're going to have a maximum current, a minimum current. You find the average of that, and then you subtract that difference from that average from the actual quiescent current, and then you divide that by the difference between the two min and max, and then you multiply by 100, and that's your total harmonic distortion. That was kind of simplistic. So I want to find out where that equation came from, because these tube equations are a big set of nonlinear equations based on the thermonic emissions, and to have such a simplistic equation like that is an approximation. So I did some more searches on the net, and I eventually stumbled on an index of a book called, what's it called? Theory and Applications of Electron Tubes, by a guy named Reich. So I started reading that book, and that book is awesome. And then I went over to tubebooks.org, and I looked for over there, and Peter's site over there, he has a little one-liner on there where he talks about this one book, what's called Theory and Applications of Electron Tubes. That's the bandwidth buster at his site. So that's probably like the most common book downloaded. And there's a really good reason for it. It's a great book. If you understand that this is written by an engineer for engineers who are electrical engineers, you can't be afraid of partial differential equations and integrals and those types of things, because it's full of that. And it starts at a very low level, very introductory level, like what happened with Forrest, back when he came up with the Triode, and he makes his way forward in time. I downloaded the PDF and I was reading it, and I remember I bought a bunch of books at that estate sale in Los Alamos. I was like, I wonder if that was one of them. So I went and looked, and sure enough, so I have it right here. I have this book, right? I was like really excited because the most downloaded book off of tubebooks.org, I have the paper copy. So I started reading this, and it's really nice to read this in the evenings because I don't have to have a tablet out, or can just kind of do it the old school way. Now this book was published in, the book I have is the second edition. It's from 1944. Now, just keep in mind, when I was reading through this, they're talking about various things, and then I realized, oh, wait a minute, they wrote this book before the atomic bomb. Because there's mentions not of the atomic bomb, but there's mentions of how things could be in the future, and it kind of talks a little bit about that. So, I read this, for a couple hours, and then I opened it up again, and right here on the front page here, it's written by, it was owned at some point by George Everhart. So I, did a search of George Everhart. And George Everhart actually worked on the Manhattan Project. He was a senior like an engineer on the Manhattan Project. This book was published in 1944. So I wonder if he actually had, I bought this in Los Alamos. I wonder if he had this book to learn about these things while he was working on the Manhattan Project. I don't know. Anyway, we have this book here today. It's a great book. Go ahead and download it. I went and the PDF version that Peter has over at twobooks.org does not have the index in it. It's just a straight PDF of the scans. So I ran it through a script that uses a thing called tesseract, that is a PDF to text OCR, optical character recognition software. And then what this script does is it goes and runs it scans, it takes the PDF of all the scans, and then it runs it through OCR. Then it merges this text representation in with the scans so that when you do a search in the PDF reader, it basically takes you to the right part and highlights over the image. It's really quite cool. So my version of the PDF has an index on it. So when I do searches, I can find it. Now, here's a couple things that I found in here that don't apply to us today because we have the power of Python and its nonlinear solvers. So on page 74, let me read you a little something around here. He's talking about determining the plate current. And he says, theoretically, it should be possible to predict from equation 3.2 the corresponding tetrode and pentode equation form of alternating current corresponding to the excitation voltage of a known waveform. So he says it's theoretically possible to determine the character, what the output waveform looks like, if you know what the input waveform it looks like on the control grid. Okay, he says practically, however, this function is called f e sub b plus mu e, whatever. He said it's so complicated in the form of equation 3.2, it is of little or no value for this purpose. The behavior of a nonlinear circuit element can in general be analyzed mathematically most readily by expressing the alternating current in terms of the infinite power series. So what they go through in this book, because they didn't have computers back then, was they develop the Taylor series expansion of the anode current based on the gate, the grid voltage. They spend a lot of time doing that. We don't have to do that because what we're going to do in this interactive demo is I'm going to show you how you can get the same results by just using a nonlinear solver. It's really quite clever. Okay, so what I ended up doing was, you remember last time I took this Mectron amplifier, the record player amplifier, and I did the complete DC analysis and found the load line. And then I was going to go show you doing the plotting, and I wrote this big ipython notebook for that. We'll go over that in a minute. And I went through the pentode section, and then I figured out that simplistic equation that was listed by Dennis Carter and also by in the RCA receiving manual, as well as in this the Reich book. I realized, those only really apply to triodes. That simplistic equation doesn't apply to pentodes. So then, all right, I don't want to make that leap. Let's just work on the triode section. So what I did was I took this amplifier and I took the 50L6 and I put it in triode mode. I did some measurements, and then I have a complete example of how to do load line placing for triodes. And then I also have a complete example of pentodes. We'll go over the triode one first, all the steps involved in going from a data sheet that only has a plate characteristic, and we are going to go through the data extraction, how to take that and actually create data points from a PDF document or from the data sheet. And then we're going to go through the code, and we'll set the bias point that we've chosen. Okay. Then we're going to play with the load line. Now remember, the load line in the interactive example will let you change the plate voltage. It'll let you change the plate current. It'll let you change the turns ratio and the speaker impedance. And from that, you can do a lot of different kind of scenarios. And while also the interactive example dynamically calculates the power output as well as the total harmonic distortion. Then we're going to go do transient analysis, and we determine from the transfer curve itself. We do a little bit of a transient analysis, so we create the output waveform from the transfer curve. And that's what Reich says was theoretically kind of useless because it's too difficult to determine. But we can do it experimentally in the ipython notebook. And then we can run an FFT on that and look at the output from the FFT and calculate the percentage of distortion. So what we're able to do from the transfer curve is to go in and verify this very simplistic equation for total harmonic distortion. So it effectively, we're on the bench, we're on the electronic bench with an ipython notebook doing things. We're not physically wiring up stuff and doing that. We will get to that point over here. But today we're going to stick only on the computer, and then at some point in this series of looking at this Mectron mod, I will get on the bench and I will use the measurement equipment that we have here and do the exact same kind of measurements over here, and to verify that, one, the simplistic equation is valid, and two, our ipython notebook approach is valid, and we will verify that on the bench and look for similarities and also look for discrepancies and try to determine where that is. And then once you're done with that, all that, then we're going to wire this back up again as in the software as well as on the bench. We're going to put it back in pentode mode, which allows us to get more power output. But we're going to look at the implication of going from a triode circuit to a pentode circuit with the same tube. Everything is exactly the same, and figure out what the harmonic content of a pentode circuit is, and see why it's different. It ultimately has different distortion characteristics, and that's not a bad thing for a guitar amplifier. So what we're going to do is we're going to do all those things. We're not going to get all that done today in this lecture. We're going to just get through this, what the ipython notebook is, and kind of get a feel for that. Then we're going to come back over to the bench. We'll measure the triode. Then we're going to go back over to the bench and do the pentode. Then we're going to come back over here and do the pentode again. Then we'll be all the way done with the biasing kind of thing, where we look at the bias point, we look at the speaker impedance, we look at the reflected impedance, we look at the load line, the slope of the load line, the placement of the load line, and the implications of that. So it's very exciting for me to kind of unveil this today. It's something I've been working on for quite some time. It's a tool that I'm going to use from now on for all my tube amplifier designs. So let's get right over to the Jupyter notebook. Well, here's how to start your writing the Jupyter notebooks. You need to go over to my GitHub page for the ValveStudio, and we need this. We need the HTTP version of this thing here, and you have two options to kind of run it. If you can run it, this thing called Mybinder, which runs your GitHub repositories online, and we'll go ahead and show that. You end up taking this URL, this Git URL right here, and you paste it into Mybinder. And scroll down and say make Mybinder. And then what's going to happen is it's going to create, using Docker or container, it's going to create what's necessary, download the repository, get it all running, and then from there you can actually launch it over here. Going this way, you're at the mercy of their load average at Mybinder, and sometimes this is great, other times it's not. So I would recommend go ahead and doing it locally. So I run a distribution of Python called Anaconda, and here's a download page for Anaconda. I just go ahead and download that, and then I run it. I do a git clone. We'll go ahead and do that now. We'll just go ahead and do the whole thing. We'll run it from Anaconda directly. So I'll go in my temporary directory and do it there. So here I'm going to go ahead and clone the ValveStudio. There's not too much to download there. Once it gets down here, what we're going to do is we're just going to cd right into that directory. And then we can just run Jupyter right from here. So what this is going to do is it's going to start up Jupyter, which is called ipython notebook, and then we're going to go to our local host at port 8008. And so Jupyter's running, and we're going to first go into projects, and here's our Mectron project. And we'll go to Triode, and we'll load the ipython notebook. Well, let's get started with this demo. Let me go full screen here. It's the Mectron load line. The Mectron is the record player I've been working on here. This is the schematic. What's shown in green are the measurements that it actually took, voltages, currents, as well as resistance. And this 225 here is the DC resistance of the output transformer primary. Here's the tungsol right from their data sheet. This is what I actually did the extraction with. Using Engage. I just put the data sheet here for our own reference. Then I start doing all the Python stuff. I don't need to go into this. If you want to go back and look at this, I encourage you to do so. But basically what we do is we take that CSV file that we just created, and I load it into as a it's called a pandas object, and we'll go through and we do a bunch of stuff with it. Anyway, let's keep going here. Then I go, just to make sure that we did all this stuff right, I go and I look at the first top of the object. Here's the first 4 rows, 5 rows, and here's the last 5 rows. You can see that I got 475 rows in my data for what I actually extracted using that Engage. Then we go down here, we set some initial initial values for our analysis. This is the plate current and the plate voltage. Here's the speaker impedance, and here's the turns ratio. So we go down here, blah, blah, blah. There's a bunch of stuff in here. You don't need to look at that. Let's just get down to the business here. The business is right. It's in this cell right here. Actually, what I need to do is when you first load up your notebook, the cells aren't actually run. So let me go do that first. So what you do is you come back up here and you say, run all. And then when you, so what it's going to do is it's going to come through here and it's going to start running these cells where the code is. So this star means it's actually executing this, and the first time you run this, it does a bunch of imports and it sets up Jupyter so that it can actually run with a notebook in the browser and that kind of type of thing. So once you get a number here, that means it's done. So we got a number here, so here's the real file, here's the tail, here's the next block of code, and then we'll go down and we'll find that the load line here. I mean, not the load line, but this is the plate characteristic. So this is the data. This is extracted data, and what this plot is showing you is a lot of information. Here are all the grid voltages, and this little dashed purple line here is the power output limit. That particular 25 or 50 L6 is a 10 watt power output. Here's our load line. This point right here is the operating point that was found. If you go back up and look at the if you look at the setting, here's 118.3, and the current through here is 48.4. So if we go down and get back down to that curve, you can see that this is where we are in this across this plate characteristic. This is our load line for the reflected impedance back into the primary, which in our case was 4 ohms times n squared, which is 33 times 33. So this the equivalent resistance seen by the plate is 4,356 ohms. The value of this is actually works out to be what the slope of this line is, because here we have plate current, and this is voltage here. So voltage over the plate current is resistance, which is this value right here. So the slope of this line is directly tied to the reflected impedance, and it goes through the operating point right here. At 0 volt gate voltage, where we would be right over here at 69 volts at 59 milliamps. And down here, if we get down to minus 40, we're at 263 volts at 15 milliamps. So this is the swing of the output voltage that's going to hit the output transformer. There's a bunch of other stuff up here. There's a power output calculation, some percentage distortion, and we're closer to saturation, which is this area over here on the graph, and this area down here is the cutoff region. So here are the 3 data points that are listed here, 69 and 59 right here. This is our Q point, and this one down here is this point here. So we're actually closer to saturation right here. So what's going to happen is if we actually run this circuit and we apply a sine wave to this, the sine wave is going to run up to this point and run back down to about here. So this is kind of where our circuit's going to operate. We're not going to get back down to here unless we can't really cross this line at all. We're not going to positively drive the grid at this point in time. Here's that simplistic equation that I was showing you in the introduction. So what I'm going to do is I'm going to move on to the transfer characteristic. Transfer characteristic is basically you take these points of these intersections and you plot the plate current versus the grid voltage. So all this code up above takes these extracted curves, finds out these intersections, and sticks that into an array. Now we're going to go down and look at the plot of the transfer characteristic. So that's what goes on down in this chunk of code. So this is the blue line with the dots. The round dots are the real data that we just got out of the curve from above. The X is a polynomial curve fit of a second degree to fit this line. And I'll tell you why we need that in a minute. But if you look at this line, it actually looks very straight. What that means is that this amplifier is very linear. We do have a little bit of a curve down here. You can see that's kind of, the slope has kind of changed a little bit. And you can actually see that once you play with this a little bit, you'll see why this is. We'll go back up here. And what you're looking at is these distance between these curves is pretty constant all the way along until you get down to here. Now they become a little bit closer together. So how that translates to the transfer characteristic is you get this general sloping up right here at the end. So triode circuits, this is a very indicative behavior of a triode circuit. There's a little bit of a slope change right here at the end, and this is what causes the distortion. And the distortion is actually only a function of the second harmonic. Mostly it's second harmonic, and that's because this slope changes here at the end. However, if we're sitting here at minus 8.5 volts, and we're going to vary our gate voltage, or our grid voltage, back and forth, we can't really go above 0, because then we'll be forward biasing the tube. So if our sine wave runs from this minus 8 up to 0, then the negative going swing will run down to about, about 17. So we're going to operate in this range right here. So this line right here is very linear. So we should see very little distortion at all. So now we're going to come down and look at the transient response and harmonic content. So what we end up doing for the transient response is we actually use this curve-fitted line, and we create a sine wave array, and we apply this curve-fitted function to it to give us our plate current. Then we multiply it times the impedance of the speaker impedance, the reflected impedance, and we get an output signal. And then to determine the harmonic content of the output signal, we run that through an FFT. So that happens down here in this section of the worksheet of the notebook. So here's our amplitude. This is the grid voltage, and this is the amplitude right here. So if you come in, let's just make this 0 for now. 0 would be straight line. So this is our quiescent point. We're at minus about 8 point, whatever we set up above, 8.5 or something like that. Oh, it's right here. Minus 8.5 is VG. This is the DC component of VG. And the output grid voltage is around 120, which is kind of what we saw way up above. If we go up and look at the DC bias point for this thing, it is, where's our, oh, it's right here. It's the top graph, the top figure. Here it is. 118.3 is the Q point voltage for the grid. Okay, so we come back down here, and that's kind of what this line represents here. Now, sorry for the coughing. You get a little drink of water. This bottom graph is the frequency response. Not the frequency response. It's actually the FFT of the output waveform. And what you're seeing here is just a digital noise, like the algorithm noise, because this is minus 340 dB. So this is just crap stuff down here. But don't even look at that yet. So with this slider up here, changes the amplitude of the grid voltage. So let's crank it up to like 4. Okay. So what 4 means, if you look at this transfer characteristic up here, we're varying on this transfer curve plus and minus 4 volts. So we're at 8, so we're running down to 4, which is about here, and then we're running back this way. So we're using this part of this curve, and we're creating current, AC current, which is going through the reflected impedance that's coming out of the speaker. So here's our output voltage here, and then this Python routine does an FFT of this output voltage, and here's the results. So the peak is sitting at 100 hertz, and here's the second harmonic content. So we're at 27 here and minus 12 over here. So that's a 39 dB of difference between these two, and at 40 dB difference between the primary and the secondary, the second harmonic. A 40 dB difference is 1% distortion. If this was 20 dB difference, that would be a 10% distortion. So we can kind of see up here, this gets all calculated up here. So here's our percent distortion, and this is our power output. The power output is the reflected power that actually gets through to the speaker. So we take this thing, this voltage here, this amplitude, and run it through the, we just do straight V times I, which is the power output right on the high voltage side, assuming it's all going to get through. The efficiency of our transformer is 100%. Anyway, I'm just kind of going off in the weeds. That's not important. So at 1%, the peak difference is 40 dB. Now remember, if we go back up to our transfer characteristic, we really can't go past 0. So we can go from 8.5, we can go up to an amplitude of 8.5 and then down to a 1 of 17. That's pretty much the excursion of what we're doing, what we can do. So let's go take a look at if we actually turn this up to 8.5. So it's going to run through some of these examples. All right, here's 8.5. So our input voltage is going all the way to 0 and down to about 17. Here's our output voltage here. So our peak difference is 32 dB right now, and that equates out to 2.31%. We will only get out 0.37 watts of power. So when we run this at the current operating point with the current load line and the impedances and all that stuff, if we run it in triode mode, we can get out 400 milliwatts of power at 2.1% distortion. So that doesn't seem like a lot. Now here's where the power of this example, this interactive code comes in. Let's go back up to the load line. The load line allows you to change the gate, the plate current, the plate voltage, the speaker impedance, and the turns ratio. So when we place this load line, what we need to do is to stay below our power dissipation. And we need this to be more in the center between this point and this point, because that'll let us to do larger excursions on the voltage. Now what that ultimately does down on this next graph is it places this operating point down more towards the center. So if we look, we're going from 0 down to 40. So what we really would need to do is to get this in the center right around 20. So we can go ahead and set that right now. With the grid voltage at 20, if we can move this point over here to 20, we'll be good. So if we get right in here, which is equivalent to 195 volts, and then we set the plate current at 50 milliamps, we'll get our Q point right there. Let's go ahead and do that. So we set 195 volts, so let's move this up to 195, and it's going to redraw this. I might do a couple steps along the way, but there we go. So we're 195 volts at 48. So let's go ahead and change this over here to 50, and that's going to kick this up just a little bit. Okay, now we're closer to cutoff. You can see that this line here is, this is actually a lot shorter because we have a data problem over here. We would need to go and extract a little bit more data out in our Excel spreadsheet, kind of extend this up. But even then, it turns out that this point here is not actually halfway between these two. We need it to really be over here somewhere. We've gone a little bit too far. So let's turn this back again. But you can see that we've gone up to 1.5 watts here. So now we're going to move it to right about there. Okay, so now we're on both the curves. Now, the other thing we can change on this is we can change the speaker impedance as well as the turns ratio. What that does is it changes the reflected impedance coming back in that the triode drives. We can do that with these two bottom sliders. So the first thing you want to try, let's try it with an 8 ohm speaker and see what happens with an 8 ohm speaker, what the effect of a load line change is. So we're at 8 ohms right here, and what that's done is it made its the slope is a lot less. We went the wrong way because now we're exceeding the power dissipation over here. So if we went down to a 2 ohm speaker, we would shift it to be a little bit higher. Okay, so now we're looking pretty good. Look, we've got our power up to 2 watts now. So that's pretty good. But 2 ohm speaker is, there's two 4 ohm speakers. Well, maybe we only want to run one speaker. You may not be able to get a 2 ohm speaker. So then let's go back to 4 ohm speaker. And we'll change the turns ratio, because this the reflected impedance is RL times N squared. So we can turn down our can dial down our value of N, which is the turns ratio. And it basically is changing the slope of our line here. So here we are with, this is our new load line. So let's go down and look and see what happens down below. We're actually, not at the power limit. So we can kick this up just a little bit more. If we go up to 190, oops, I went the wrong way. That's not what I wanted to do. That was at 180. Okay, so we're right. Let's move this up about half of, well, that's a quarter of a tick. We can go a little bit more. Okay, so now we're kind of kissing this power dissipation curve right there, and we're at 2.17 watts. And look at our distortion went down to 0.3%. So this equation here is actually fairly accurate when you have this section of the load line, the distance-wise, is the same as this section. This is fairly accurate. When we come back down, this graph isn't dynamic like the other one up here. You have to rerun this cell. The way you do that is just click in the cell and hit the shift and return, and it's going to regenerate this plot. So now here's our new operating point, minus 16 volts at 55 milliamps. And we're going to go ahead and rerun this transient response as well. So now, this is the same thing as before, but it's actually using the new transfer characteristic. So you notice that VG was 8.5, now it's 16.9. So we can actually drive more signal into it, and we can get up to 16.75 before we start topping out at VG equals 0. And now we're at the peak for the output swing here is at 38 dB, and the second harmonics is at about 15 dB with a 23 dB difference, and our distortion has gone up to 6.8%. But our power output is 1.77. So this analysis, we're not quite going on the complete excursion of this waveform here, and we're not really fully swinging here, but that's okay. That's okay. So now the last section on this notebook, all the way to the bottom, is it takes all the parameters that were calculated, and the JavaScript code comes through and creates this output waveform at the drive voltages of 0.1 volts, 4 volts, and 8 volts. And what that does, and then it actually is going to comes down and creates these. It creates an array in JavaScript, and then the browser is actually going to play out of the browser speaker this waveform here. So what you can do is listen to that waveform at different input voltages. And let me turn on my volume over here. Okay, so this one is the one that has very little. That one has very little distortion on it. These might all sound the same to you, but I'll show you why they're different here in a minute. And what this code does is it normalizes the audio output level so that they all at the same, the fundamental is at the same amplitude coming out of your speakers, but the distortion content is different. So what this is actually ultimately letting you do is listen to the different waveforms at 3 different input voltages so that you can see and determine for yourself what the impact of harmonic distortion is right here in the browser without having to really wire up anything. What this really ultimately lets you do in this example, let's kind of go over this whole thing here. You can take your schematic, you can take your tube data sheet and extract data out of it and create this graph. These series of curves, extracted data. Then you come down here and it will plot your load line with the Q point that you determined either experimentally or through data sheets and theory. And based on the speaker impedance and the turns ratio of the output transformer, it plots this curve. And from that, the intersections here create the transfer curve. And this transfer curve here is nonlinear, just barely, and that is going to affect the distortion figures. Then down here, we actually look at the distortion based on different amplitudes of the grid voltage coming in, the AC component of the grid voltage, and we look at the frequency, their harmonics, and the content of this waveform here. And then finally, at the end, we can actually listen to these. You can be a judge for yourself. You know, if 1%, 2%, 10%, whatever where your ears actually can distinguish distortion. So let me show you one more thing here, and then we'll kind of wrap it up for today. What you're looking at is a spectrum analyzer. It's called Sound Analyzer. I got this over at the Google Play Store, and it's running on an old tablet that I have. You can kind of see that it's digitizing my voice as I speak here. So I like, ooh. Okay, so you can kind of get the point. It also has peak detection there for the primary, for the very peak. So what I'm going to do is cycle through these voltages for the grid voltage, and we're going to look at the harmonic content coming out of our graph for the transfer characteristic for this triode. So here's 0.1 volts. This is a very low signal, but remember now these have been normalized so that the fundamental is at the same level. So that's about 63 dB. That was 0.1. Here's a 4 volt drive going in that's normalized. So you can see our secondary there was well, let me see, how far down was it? So we're at 63 here, and we're at 30 here. So it's like 30 dB difference between these two. Let's turn this back on again. Here's an 8 volt drive. So that ended up being a little bit more second harmonic. Now here's 16 volt drive. This is the full excursion on our optimized design. And we're going to look at the amplitude of the secondary, the second harmonic. So this is 65. We can actually like pull a cursor along here and we can see what that value is. It is 44. So we're down 20 dB. So if we powered up and put a 16 volt peak to peak signal into the grid, we would get out that a output waveform that had this 20 dB difference here means that we're at 1% distortion. No, we're at 10% distortion because it's 20. So that's pretty good. So what we're doing on this graph here is we're using a free sound analyzer off of the Play Store, and I'm sure that the iPhones have the same kind of thing. And looking at the harmonic content, you may not be able to distinguish this with your computer speakers, but we can definitely, this piece of got air quotes going on, test equipment is showing us stuff that that's pretty valuable in our exploration of this triode circuit. This is all done through simulation. We haven't got to the bench yet, but we will in just at some point in the future. Wow, today's episode is a marathon. If you made it this far, you're a trooper. We covered a lot today. We covered a little bit about history and how one statement in a YouTube video spawned me into looking into finding the reason where the simplistic equations came from. And I came across a really good book, and I'll have those listed in the show notes. Go ahead and encourage you to download that. If you didn't go follow along with the Jupyter notebook during today's video, I encourage you to go do that. It's very informative to go in and actually play around with the triode circuit that I have in the notebook currently. And we took that and we actually looked. We gave an estimate of the performance of this thing when we put it in triode mode. And then we looked at if we had the option of changing the turns ratio on the transformer or the speaker impedance. That's probably the easiest thing to change. And the anode, the plate current and voltage. If we go and change those around, we go from 400 milliwatts, 0.4 watts, up to 2 watts possibly when we're running this one tube in triode mode. There's quite a bit of significant difference there, 4 times the power. But all that's unrealistic for several reasons. One is this design is kind of fixed. This is a inexpensive project that I wanted to keep on the inexpensive side. So I'm not going to put another output transformer in there. I'm not going to work on the power supply circuit. I'm going to live with what I got here. So I was doing the optimization. I was just demonstrating the Jupyter notebook to show you how to do it. And we're going to be using that as a tool in probably all the future designs that we do here at the ValveStudio. But at some point I want to get to the bench. It's critical that we get away from the computer and we get to using the soldering iron. We actually make something. We've been doing that a little bit on the Mectron amplifier. And that's a good thing. And I got my equipment out here and we're ready to take some measurements. But I'm not going to do it for the triode mode on this particular design because I'll never use it for that. What I do want to do in the next segment is I'm going to put it in pentode mode. We're going to go through the exact same kind of thing with the Jupyter notebook, maybe not as long as it does this one. And then we're going to get over here on the bench and actually verify the measurements that we get out of our circuit analysis using the Jupyter notebook. So we covered a lot today, and if you liked the content today, there's plenty more where that came from. I'll let you know that going through and looking at the journey of this learning process for me is very exhilarating, and I get a big thrill of reading about history and finding these old books and actually getting to apply current tools and techniques like this nonlinear solver in Python to the problems that they had back before, during the World War II, and solving those problems using something that's, it's almost literally free today. So these guys, when they did it in the old days, they really knew what they were doing. I want to get a glimpse of that knowledge, pass it on to you, and you can use some modern tools and make the amplifier that you want. So that's what I got for today. Thanks for watching, and this is the ValveStudio. That's all for today.